Welcome everyone to our webinar series on acoustic, mechanical and thermal metamaterials. Today we have the great pleasure to welcome Professor John Willis, who is a fellow of the Royal Society and who is famous for the Willis Media after his name. And today Professor John Willis is going to talk about reflections on constitutive relations for acoustic metamaterials. John?
Okay, thank you. Well, I wish I could see whoever is there, but I'm very pleased you are there, whoever it is. You see my title. Sebastian he regards me as a historic relic, and he wanted me to say something about the origin of this coupling business, which I guess I introduced. And so that's my excuse for the first couple of transparencies. The first one is called Ancient History. This is really how I came about this subject in the first place. Now, in the 70s, I was interested in effective moduli of composites, and I was interested in random media because periodic ones, it seemed to me, you could just compute anyway. By the way, computing wasn't nearly as powerful in those old days. And the thing that I was most conscious of was the famous Hashim-Strickman bounds, which, by the way, were first developed in the electric context and only subsequently done for elasticity. And so I guess it was probably Strickman that had that kind of motivation to formulate things in terms of polarizations. And you all know what electric or magnetic polarizations are. And of course, there's going to be a background medium, usually a vacuum. But another thing you can do is make it any old comparison medium you want. Okay, well, my contribution there was to take hold of what was known as the Hashim-Strickman variational structure and turn it around into a form where I could explicitly deal with any two-point correlation I wanted to put in. And I was able, by using that sort of twisted around formulation, to find some bounds for random composites with anisotropic two-point correlations. It hadn't been done before, so that was it. There was no theory of homogenization at that time. It was under development. So people were talking about effective properties and solving boundary value problems with sort of uniform boundary conditions applied to them in some way. But of course, homogenization was coming along, but it wasn't available for random media until the 1980s. And I didn't attempt to join in that. I thought the professional analysts were going to be better at it than I would be. I was more interested in trying to get results for, particular classes of materials or something. Anyway, I did that. And by the 80s, I was interested in, well, how it could be generalized, if you like, or developed further. One thing that concerned me a lot was, could I develop this for nonlinear composites? And I did manage to produce a variation on that, and it became quite a big industry for me, one or two others. But the other concern, more relevant to today, is that I was a bit interested in what would happen when all of this homogenization theory, which was under development, was going to fail, when the separation of scales condition wasn't going to be met. That means I'd be interested in disturbances with fairly short wavelengths. And it seemed to me that the best way of entering that was to admit dynamics, because, ultrasound or something, you can make wavelengths more or less what you like. So I was motivated that way to consider the propagation of waves through random media. There was a little catch, that is, computing power was not very great, as I said, and so I was more in practice going to look at asymptotics for fairly long waves, but try to get out corrections for dispersion and attenuation, which I was in a position to do because in the course of what I'd done earlier, I'd sort of found some tricks for finding a good representation for the Green's function. And I could generalize this to dynamics in a form that was very suitable for that kind of perturbation theory. Anyway, you've possibly read what's on the screen. The gap which I was concerned to try and fill was in the regime where there was large contrast and the wavelength of the disturbance was going to be similar order to the material's microstructure dimension. And there was direct interest in that regime, for instance, for non-destructive evaluation. What I did, of course, was to do something with the Hashim-Strickman type of approach. And so my contribution was to develop and exploit that generalization, which I managed to find. And thereby I was able to obtain approximations for effective relations for dynamics of composites. I describe them as honest because I give a definition and I follow it through with precision, with honesty, if you like. It doesn't prove actually that you're going to see this in a particular composite. I dare not say more about that now or I'll never finish this talk. Okay, but anyway, I'm going to talk about that kind of development, and a bit towards the end of the talk, I'll take up this other point. Actually, by the present time, there's a lot known about the propagation of waves in bulk composite, even for random media. So I've said there it's mostly well established. But the question is, what happens near a boundary? And basically, at least the way I've defined effective relations, they're non-local. And so the presence of a boundary is going to screw up the relation. It's going to make it different. So there's something you need to do, something to worry about at least. And I have worried about it a little, and I've made a little bit of progress, that's it. Now then, I'm not going to discuss elastostatics from first principles. What I'm going to do is to look at dynamics, and I'm going to take Laplace transforms. There's a Laplace transform variable S, which replaces d by dt. And what you can see here, near my cursor, if you can see it, is the equation of motion. The divergence of the stress plus the body force equals the rate of change of momentum density. And constitutive relations are that stress is related to strain. The elastic constant tensor I called L, and because it has symmetries, I can write L times grad U if I want to. And P, the momentum density, is density times velocity, which turns into density times S times displacement. Well, if you plug relations through into the equation of motion, you get the usual second order equation, which you see here, except I've got S squared instead of D2 but ET squared. And if you like, you won't see much in suffixes, but there it is in suffixes. Now, this equation of motion is going to apply to a body occupying a domain omega, and I've got to put some boundary conditions on it and some initial conditions. The initial conditions are actually going to be 0. And if you adjust the body force, if you're prepared to put delta functions on, of course, you can simulate other body conditions directly, immediately following time 0. As far as the boundary is concerned, you could either give all components of traction, or you could give all components of displacement, or you could give some kind of complementary mixture of both of them, not necessarily the same at each point. And those are the kinds of things that I'm thinking of. I'm not going to describe it further. Now then, the second order equation, which I wrote down, you can write down an energy-like functional immediately from it. It's this thing here in the red box. V is S times U, of course, because I'm using that notation. I'm using Laplace transforms. And that principle, the stationarity of that thing, actually delivers a minimum if S is real, because then the integrand is convex. What about these things, sigma 0 and P0? Well, it's my way of incorporating the boundary conditions. Sigma 0 and P0 are any stress and momentum density fields that satisfy the equation of motion, which I'm trying to gesture at now. It's underlined in green. Okay, it doesn't have to be related to a displacement or anything, but it's just that equation of motion that's satisfied. And in addition to the equation of motion, any given boundary conditions on traction have to be satisfied. And really, I'm going to look for stationary points of this, but I'm going to talk about minimizing because it's kind of convenient to do so. And that's what it really is if S is real. But if S is complex, it isn't. It's just looking for stationary points. This is just notation. I've called curly L the elastic constant tensor and rho, and nothing on the diagonal. So this is like fourth order tensor space. Rho is like second order tensor space because rho relates velocity, which is a vector, to momentum, which is also a vector. Of course, it's a scalar in the case that the tensor is the identity, which it usually is. So people don't realize. The energy functional, which I just showed you in this sort of matrix notation I've introduced, is right here. And that's sort of saves me a bit of work for the future. Now, if the medium's random, what I've described so far is what goes on in any particular sample. Let's label any particular sample alpha, which is a member of a sample space, which actually I've christened A here. And there's a solution now U, which depends on the sample as well as on position and on S, which I've suppressed. And the solutions picked up for every sample simultaneously if you could manage, which of course you can't do really, to minimize the ensemble average of this energy-like functional, the thing that's here in the red box again. P is just the probability measure associated with the sample space. Okay, so if I could minimize that with respect to all admissible U of X and alpha, I'd have solved the whole problem in every member of space, every sample. But now what I'd like to do is to consider this. Let's first minimize this ensemble average E subject to the constraint that I'm prescribing the mean value of U. Okay, and once I've done that, I'll minimize the result with respect to the mean value of U. Well, if I do the first minimization, I'm going to get a quadratic function in E and V, mean values of E and V, because it's the mean value of U that's prescribed. There's going to be something in between, which I've called L effective here, minus the sigma 0, P0 you saw before, operating on mean value of E and mean value of V, which is a functional just like the original one, except it's L effective instead of L, where I'm now pointing. It's also, if you do this sort of thing, you can follow the reasoning. You can also calculate the mean value of sigma and the mean value of P explicitly, and you can confirm that you can get the same L effective as the one that I introduced here. So there's not really a problem with that. Now, the if is actually defined only by the quadratic bit. It's the minimum of this thing, subject to the constraint that the mean value of U is prescribed, which actually is a good stochastic homogenization principle as well. It's not usually written that way, at least I don't think it is, but it is entirely consistent with what the probabilists do. Now, also, this L effective is an operator. It's non-local, and it's not uniquely defined. So I'm integrating not only over space, but this thing is also non-locally operating on this E and V here. Okay, so there's two integrals involved. And the problem is that L effective, it's easy to see that it's not uniquely defined. If it was just constants, it would be. But if it's functions, it isn't. Oh, look, I lost something there. Okay. But the corresponding mean value of sigma and the mean value of E and the mean value of V are unique, even though L effective isn't. But there are ways of getting over that problem. Here's one particular way. Suppose that I want, this is a reasonable thing, that mean value of sigma and mean value of P, sigma and P are L and rho times E minus eta. Now, what's eta? You'll see on the next slide. I'll tell you now. It's some sort of inelastic strain, okay? And if I want that to hold even in the case of the mean value, in the case of the averages, okay, if eta is short, I want that to work. That will then fix this uniquely, because if I bung this eta on the end of this thing is no longer a compatible strain. So it's completely detached from any displacement, and it's completely detached from V, and that changes the possibility of getting non-uniqueness. Now, if you make that definition and no other, you can actually get this explicit formula here, which don't worry about too much. I'll just put up the next thing, which puts the notation on. What's E suffix W? Well, first of all, you calculate not just the average U, but you calculate a weighted average of U, where the weight is 1. Yes, okay, it's a unit weight. So you calculate a weighted average U, and you calculate the strain associated with that. And you also calculate the velocity associated with that, which is S times it, to get VW. And that's what the notation kind of means. And well, I tell you the truth, when I first was playing with this, I tried to do this with variational principles, and I tried to do it with a comparison medium, and it was too hard. I couldn't do it. So I had to resort to calling Green's function the Green's function for the actual random medium. So G is random. Okay, I don't know it, but nevertheless, you can probably believe that G exists in every sample. So you should believe that this formula actually means something. I'm not going to say too much more about it. Now, that's a bit of a digression. I'm going to carry on with it. I've gone off variational principles for a moment. I will come back to them. And the way that I came by this in the first place, honestly, was through variational principles. And then I had to make this resort into something else. But having got this far, having got this formula, it seemed worthwhile to try and work it out in a simple case. And this is the elementary example I did. It was a one-dimensional periodic medium, period L. Okay, that is different from the elastic constant thing. There's a green piece and there's a red piece, which have different properties. And I also shoved a point mass M into what here is the green piece. And then it's easy to solve that problem because you can calculate the Green's function and you can calculate its ensemble average. It sort of involves Fourier transform theory and Fourier transforms. And I was interested in, well, let's put it this way. I realized that this stuff would possibly be some use if the wavelength of the effective wave was much longer than the period of the microstructure. In other words, a sort of homogenization limit, even though the presence of this mass would ensure that this phase was jigging around all over the place. Nevertheless, the average wave should have a wavelength which is longer than L, significantly longer than L. So I went to the extreme with that and looked for zero wave number components. Now, it was pretty obvious for all sorts of reasons, from the variational structure and the Hashing-Strickman and so on, that L effective was not just going to be sort of diagonal, it was going to have some other stuff, which I called S and S dagger in there, which would couple stress to velocity, and there would be another one, which I call dagger, which would couple momentum to strain. Now, in the case of self-adjointness, of course, this is going to be the adjoint of this, but more generally, the formula I showed you before would even be true if there were no variational principle and if the problem were not self-adjoint. In that case, this thing would not be the adjoint of this, but if the whole problem's self-adjoint, that's what you're going to have. Now, coming back, I didn't really want this S to be zero, and that's why I put this mass off the sort of middle position, the middle of material one, because I did not want the composite to have reflection symmetry, because if it did, in the zero wave number limit, that term would be zero. Now, the reason why I've just labored this a bit is that I know that Andrea Alou gave a seminar a few weeks ago, and one of the things he was talking about was non-zero coupling if you had a failure of reflection symmetry. I'll say no more about it. I will say one other thing about Andrea, though. I showed, oh, these are pictures. Look, this is the C effective at 0 wave number. This is the ordinary definition. And this is if I've only done the averaging, I weighted this phase 2 so that I'd only be averaging over phase 2. So this stuff, which was jigging around, wouldn't participate in the average, which doesn't seem completely unrealistic. So this is also C effective. And I'll say something here. Look, there's a resonance. And you can see some negative C's there. But look at this. There's a resonance, not quite in the same position, but it's the curve's turning the other way. Well, it wasn't quite in this context, but I gave a lecture in St. Petersburg, and Andrea stumped me afterwards at the end of the talk by pointing out that if I had things like that, they couldn't both be causal. What he meant was they couldn't both be causal and dissipative at the same time. One would have to be energetic. I knew they were because of the way they were constructed, but I didn't really have a very good answer to him. Oh, these pictures on the next slide, this is the effective rho, and these things are the effective S. Blue is real, green is imaginary. Blue is real, green is imaginary. So the rho effective is real, S effective is imaginary in this limit. Okay, well, having had this difficulty, I also did some calculations later for a medium with a bit of physical attenuation in it. And these plots here are for C effective, S effective, and rho effective. I suspect I've got the colors wrong here, but I apologize for that if I have. It was for a pretty small wave number, 0.1 relative to the period length. And the reason why it isn't that one particular component has to be sort of dissipative, it can even pick up some energy from the other component. This is a weighted average here, I think. Yes, the weighted average over phase 2. It can even pick up the other component, so long as the total of the potential energy and the kinetic energy is always going to decay. You're in business and it's fine. And that's the fact, it is. Oh, this last plot here is the difference between this thing calculated one way, the way I first did it, and another way, the way I second did it, using the formula that I actually showed you. So that this C effective is different for one calculation than for another. And this is just a plot of the difference of what the stress looks like if you use one calculation or the other. It looks pretty bad, except for the fact that the scale here is 10 to the minus 6. And the reason for that is that I kept about 100 terms in a Fourier series. I'll say no more about that. I'll get back to what to do with a 2-dimensional or a 3-dimensional random medium. Now, most of this slide is a reminder of what I showed you before. This is the variational principle, okay? And I want to minimize it by the actual display. I want to minimize it, okay, or make it stationary. If S is real, I minimize, okay? Now what I'd like to do is to introduce a Legendre transform. Instead of having L here, I'd like to have L minus L0, where L0 represents a comparison medium. And then I would like to split this thing up into L0 plus L minus L0. And then the L minus L0 part, I would like to subject to a Legendre transform. That's why you see L minus L0 inverse and rho minus rho 0 inverse here, and some corresponding variables, tau and pi. That really is stress polarization, if you know that terminology. That really is momentum polarization, if you know that terminology. You can see there's quadratic in tau there, there's linear in tau there, so if you looked at the stationary point, you'd get back to where you started. Okay, that's said enough there, I hope. Now, if I make that functional h stationary with respect to tau and pi, I reproduce the original thing E. And for a random medium, if I made the average of H stationary with respect to Tor and pi, now depending also on the sample space, that would reproduce the expected value of E. But let's do it the other way around. Let's first minimize, or make stationary if you like, it is actually always minimize, the mean value of H with respect to U. And if I do that, U and X, and this is formal, I don't know how I do it in practice. If you go back and see what was involved, that's related to U, that's related to U, that's not. So there's a U there, there's a U there, and there's one there, there's one there. Well, that's just a problem for the medium with properties L0 and rho 0. So if you solve that problem, you'll get a solution which is deterministic, it's U0. But then there's the other stuff that comes from the divergence of Tor and the time derivative, or S times pi. And so the Green's function is the Green's function of the comparison medium, though. So there's the solution. There's a contribution from boundary terms. I'm not going to mention them, and they're a complication. If you do this, then now E and V, if I differentiate this, are going to be E0 and V0 minus whatever I get from G naught times operating on the divergence of Tor and pi dot. Okay, so you see it there. Okay, well, if I know that symbolically, what are these things? Well, they're derivatives of G0. Symbolically now, I call this thing curly S, so there you are. Now what I'd like to do is to average this to obtain what you see at the bottom here. I hope that the average of E and the average of V is E0 and V0 minus S times the average of Tor and pi. Now I can turn this first thing around and replace E0 and V0 by average of E and average of V and get the thing right here. Okay? Now the thing about that is that it actually involves average of E and average of V, so it'll give the conditional minimizer conditional on prescribing the average of U. By the way, there is a version of this with weighted averages, but it's more complicated. I have done it, but I'm certainly not going to try to show it to you now. It would turn you off. Okay, so there we are. Now let's look at the conditional stationary value of the average of H. Okay, that means I substitute this thing into the functional. And if I do so, I get this nasty long mess here. Some of it is already sort of determined. And there's this stuff here that still needs some attention. So now if I make this expression stationary with respect to Tor and pi, okay, I can do that. It's quadratic or linear, okay. Tor and pi will be related linearly to E and V, mean value of E and mean value of V, through some operator, which I've just called curly T for the sake of calling it something. Goodness knows how you would actually solve that problem. But if I do that, I'll get the total sort of stationary point of H. It's the same as the effective value of E, if you like, and that's a definition. And it's going to be what I had before, the stuff that you could see, plus the stuff that I've just been talking about. And in fact, if you make something like this stationary, the whole thing turns out to be just 1/2 of the linear term. So that's why it doesn't look too bad. That's why it contains that. Now, if you can recall, I'm not going to show it again, in the general expression, E effective was going to be like this, except it would have L effective in here. So this is L effective. Now the crunch is I can't find it exactly, but we can find a Hashim-Strickman type of approximation. By the way, this kind of formalism makes it obvious that there's no way this thing's ever going to be just diagonal. And that's really the way I first came by this observation. Now, I need to make an approximation. I don't want it to contain more information than I have. Now, the random medium itself is going to have n different phases, different materials, and they're going to have characteristic functions chi r, which of course will depend on the sample space. They'll be in different positions. okay? But there's LR times chi r, or there's rho r times chi r. And I'm going to seek an approximate stationary value of this h thing by taking not the most general possible torr, but something that is of a rather similar form to this. Torr r, if you're in phase r, still varying with position x, and pi r, if you're in phase r, for the pi variable. And you'll notice there's still chi in there. So this is a prescription for an approximate description of every sample of the random medium. But now I can plug that into the functional and I can average. And if I just mention this, it's going to contain quadratic terms. And so I'm going to be interested in, well, the average of chi by itself. And I'm also going to be interested in the average of chi r times chi r dashed evaluated at a different point, okay? And here, if you like, is a covariance psi r dashed, which is defined here. And if I introduce that definition into the functional, it looks as you see it. This is simple. This is pretty simple. And this is the stuff that involves these 2 points. And that's what it is. PR, of course, is just the probability of finding a certain material at a certain point. Okay, that's it. That's all you get. But having got that far, I can now try and make that thing stationary. And if I do, it's not going to be exact because I wasn't looking in a big enough space. But it's the best I can do if I only know 2-point information. Oh, that S psi with a curly bracket in it is an integral operator whose kernel is the product of the integral operator S with psi r prime. And if the medium's infinite and statistically uniform, the Green's function is going to be a function of x minus x dashed, and this thing is going to be a function of x minus x dashed. That's for uniformity. In that case, the operator is a convolution operator in space, and the equations defining the torr and the pi can be Fourier transformed. Then they become a system of algebraic equations. Fine, good, if you can do the calculation. But now if you go specialized to the case when n equals 2, there are only 2 phases. Now, chi 1 plus chi 2 in that case is going to be 1. And therefore, these psi 1, 1 and psi 2, 2 and psi 1, 2 and psi 2, 1 are all going to be expressible in the form that I show here. In terms of one single function, I've multiplied by P1, P2, I'm calling that thing a correlation function. I think I am anyway. And it's easy enough to check that when x equals x primed, you've got to have one material at one point. H of 0 is going to be 1. And another thing is that H should tend to 0 as separation tends to infinity if the composite has no long-range order. Now, in fact, it'll be sort of negligible if you go a couple of correlation lengths, whatever that means. Okay, so anyway, if I specialize now to a 2-phase medium, I get down to this point. I get down to the point of just 2 equations, and I've written them out in terms of the jump in torr and pi and the average of torr and pi. Okay, the definitions are right there. The first equation here only involves the jump, so I can solve it formally. There. H0, of course, is S times this correlation function H. Okay, there's a funny definition here. L hat is P2 times L1 plus P1 times L2. It's sort of well known in Hashim-Strickman technology, if you like. So anyway, there's the first equation solved. You substitute that solution into the second equation, then you can solve that one. You get this, and you notice here I've got the average of L minus L0, and then I've got some other stuff. But L effective was, this is the operator curly T, and L effective is L0 plus average of T. So L effective is displayed right here. So that, if you like, is the general theory. And in the course of that, I've told you, I guess, most of what I know. Now, I had my other computer telling me the time it switched off. So if I look as though I'm getting too slow, I'd be grateful if I would be G'd up. Okay, so there's the basic theory. Now I'll show you some results, more recent ones. Originally, I was preoccupied with the Hashing-Strickman formalism and doing perturbation theory and so on. Of course, I was much too thick to realize that this stuff was useful for the kinds of things that nowadays are so popular. I didn't realize that such things would be in existence even, unfortunately. Anyway, what I'm going to do now is show you some implications of this formula. For a very simple example, it's going to be a scalar problem rather than a tensor problem, which this is. Here it is on the next slide. There's my little effort at drawing some kind of random medium. These inclusions are unfortunately all the same size and shape and same orientation, but that's just my drawing capacity. But you can see they're pretty random. I'm going to choose both phases to have the same elastic modulus. This is an acoustic material, so U is just a scalar. And the densities of each phase are going to be different, ρ1 and ρ2. The question is, if I propagate waves through that material, what's the dispersion relation? Well, I'm in a good position to answer that because look, there's a general formula. If I can substitute into it in this simple case, I'm going to get what I want. Well, for this composite, I'm choosing the same elastic constant for each phase. So there's only going to be a polarization tau because the mean stress is going to be the average of mu times the gradient of U. But mu can come out and give me mu times the gradient of the average. So the mean, there's no coupling in this, unfortunately. There's none of this off-diagonal coupling because it's a scalar problem. Anyway, there we are. I get these two equations. You could solve them. There's the solution. There's the formula for rho effective, which is a special case of the general thing I showed you before. Now, that rho effective thing, if I choose S to be real, and if I choose ρ0, the comparison medium, to be the greater one of ρ1 and ρ2, the formula will be an overestimate for rho effective. It'll be an upper bound. And if I chose ρ0 to be the smaller of these two, I'd get a lower bound. Now, for this scalar problem, there's the Green's function. It's just exponential divided by r, basically. There's the wave speed. Its Fourier transform is dead easy. It's that thing. But now if I adopt this correlation function here, this is deliberate, and I multiply that by g, I just change the exponential factor. So immediately I know the Fourier transform of this h. So there's a dirty trick. It shows how lazy I am, I guess. But what I'm going to do in the future is just look at that special case. So with that, and with this notation, I'm calling this thing H0, the dispersion relation, which of course is just mu k squared plus rho effective times S squared 0, that's going to reduce, it does reduce, if you plug in the algebra, to a quadratic equation in k squared, modulus of k squared. There are two possible values for the modulus of k squared, and there are the formulae there. So this very simple composite is going to give two kinds of plane waves, mean plane waves. Not one, two, exactly two, not three, not an infinite number either. So there you are. I think that's kind of interesting. Oh, before I show wave speeds, I'm going to take S real and just show you plots of effective density. There's an upper bound. I said how to get that. There's a lower bound. And this one was obtained by taking ρ0 somewhere in the middle, by taking it to be the mean value of rho, which, by the way, is what they all tend to at very low S's, low frequencies, if you like. Okay, except this S is real. So this is something in between, so it must be a bit better, I suppose. And the truth is, I don't know how to choose a ρ0 any better than this. And so this is what I'll be recommending for the time being until I dream up something else, if ever. And it's certainly true for the rest of these sort of slides. Now, wave speeds. If I choose S equals I omega, of course, I no longer have bounds, but I've got approximations. This particular set of plots is for a ratio of densities of 10. Row 1 is the less dense material, and it's there's only 15% of the more dense stuff. So if I choose row 1 as the comparison medium, it's like a matrix with inclusions in it. That shouldn't be too bad. We know it's not right because you saw from the bounds it isn't right, but it's not really not too bad. The alpha wave is the one which has zero attenuation at very low frequencies. That's the way I defined it. Otherwise, it's defined by continuation. Okay, and the beta wave is the other one. And look what happens at low frequencies. It's got a huge amount of attenuation, imaginary part in it. It's also got the penalty that the real part depends on the choice of comparison medium, whereas with the matrix comparison medium, you get this. So anyway, the red curves here would be my best shot at what I think the answer should look like. And that's where it is. So you see that I've got two waves, and at low frequency, there's one of them attenuate slowly, so that's a propagating wave, and the other one will attenuate fast, and well, that's an evanescent wave. They're all evanescent a little bit for a random medium. Okay, but at higher frequencies, it's less clear cut. Look, this versus this, there's not so much in it. They're both attenuating. But already you see there's something about effective medium theory. If I go through it, and other approximations may not give two waves, I should emphasize, but all I'm saying is that you can get a surprising number of waves, surprising in quotes. And it's a consequence of the non-local response. Now here's the crunch. If any boundary is present, the non-local response functions won't be those in an infinite medium. And if all of the waves are omitted from the study of the infinite medium, and then you try to solve a transmission reflection problem of some kind, you won't have enough conditions of continuity to determine all the transmission and reflection coefficients. And the only way I could really think of to resolve this problem was to solve the whole problem some way. And there, of course, to do that, I've fallen back on my variational methods. Okay? Everything I showed you was actually for a finite body omega until I specialized it to an infinite body. And by the way, I was careful to set up that formalism with the averages subtracted off so that the integrals, if I went to an infinite body, would converge. So that boundary terms, if I had a finite body, that the integrals would still be sort of convergent and localized by the correlation of the medium. Anyway, so I've solved next the following problem. This is the medium you saw before, except now I've sawn it off at x2 equals 0, and I've stuck it onto a homogeneous medium with more properties again. All the density, all the materials are going to have the same modulus, but they're all going to have different densities. So I've got row 1 and row 2 in this, and row 3 in this. Now what? Well, try solving that. I can generate from my variational principle a system of integral equations, and it is a Wiener Hopf type. It's a matrix Wiener Hopf problem. But at least for this correlation here, the simple one, and it's the only one I've really looked at, the system can be sort of pushed around a bit, and you can solve it explicitly. It's still, I found it a hard calculation. I say it's fairly difficult. It was hard for me, but I did it. And this is the result. You put in a plane wave from the homogeneous material, okay? So you'll get a wave reflected into the homogeneous material with amplitude R times original amplitude, so reflection coefficient R, and the disturbance generated in the composite, x2 positive, will only consist of an alpha wave and a beta wave. There won't be anything else, in spite of the fact that the formalism didn't a priori exclude it. But this is when you solve the problem, you get two transmission coefficients, T alpha for the alpha wave and T beta for the beta wave. After a lot of work, that's what I got. I wouldn't worry about it. I'd just say that it shows that this is a problem with closed solution. By the way, K1, which dictates the angle of incidence of the incident wave, is contained in G3 and H0 as defined here. They're slightly modified from the ones I had for the infinite medium. And so everything is there. Now results. This is a composite. Rho 2 is 10 times rho 1. The lower half space actually is material 1 again, although it didn't need to be, and it's 15% volume fraction of phase 2. And it's normal incidence. And so I've done this with two choices of comparison medium. One, rho 0 is rho 1. That means that the lower half space didn't have any polarization in it. And secondly, rho 0 is the mean value of rho. But then there are three polarizations. Well, these are the transmission and reflection coefficients. This is when rho 0 is rho 1, real part, imaginary part of the alpha wave. For the beta wave, there's nothing at low frequencies, but at higher frequencies it comes in, it becomes even bigger amplitude than this thing. Of course, as you go away from the interface, this thing's decaying, but then they're both decaying about the same at higher frequencies. So it's hard to say what's going on. And then there's a reflection coefficient, real part and imaginary part. If I do it with rho 0 is mean value of rho, you get more or less the same picture at low frequencies, but at higher frequencies, you get a noticeable difference. Look, quite different. And I don't know what to say about that, except that I prefer this. I do believe that it's more reasonable, to at least to hope that that's a reasonable representation than the other one, because of what it showed for the bounds when S was real. Now this is a very similar picture, except now rho 3, the half space below, was average material, and that means you've got acoustic matching at low frequencies across the interface, which is why you've got 1 for the transmission coefficient initially and 0 for the reflection coefficient initially. Otherwise, the pictures are rather similar. Now this one is, it's the same kind of plot. I've chosen a frequency omega A over C1 to be 0.3 just for the sake of it, and I varied the angle of incidence, and this just shows that the formula works for it, that's all. Okay, now this one here, it's a 50-50 mixture of materials with a density ratio of 10, and rho 3 is the mean value of rho, to save anything else. Anything else to say about that? Not really very much, except, of course, I really wanted rho 3 equals mean value of rho now, because when they're equal fractions of each material, what else could you hope to choose? Now, here's a final question. It's the two transmitted waves which forced me to solve that whole problem. Now, suppose that I didn't even realize there were two waves. Suppose I thought there was only one because I'd done the calculation a different way. And of course, this would have been the alpha wave because that's the one that is reasonable at low frequency. And so suppose I just allowed for that and nothing else. Then I could solve the transmission and reflection problem perfectly well, directly. And I get an approximate reflection coefficient R suffix A and an approximate transmission coefficient TA. Now I'm comparing those with the full solution on the next slide. There's the correct T alpha. There's the TA. There's the correct R. And there is the RA, the approximation, so on. Okay. So that's the plot at normal incidence, I think. This actually was a configuration where rho 3 was equal to rho 2, but it's just illustrative, that's all. Okay. So you see, if the frequencies are low, this approximation, just neglecting the beta wave, is fine. But if the frequency goes up somewhat, it really is not going to be so good at all. And this plot here, I think, is against angle of incidence, and it's at a frequency of omega A over C1 is 0.5, so it corresponds to about here. Okay, so this is zero angle of incidence, so that corresponds to this, and now you change the angle of incidence, keep the frequency the same. Well, those are the results. Now some concluding remarks. I should say I don't have a clue what the time is. You can enlighten me in a moment. First, I'll say this. The analysis that I've done is exact, but that was analyzing my equations, and the equations are approximate. I do believe it's a decent approximation. If you only know 2-point correlations, I don't quite know what else you can do, but it is an approximation. But after that, what I've done is exact. At low frequency, they illustrate perfectly well that there's one dominant mean wave. And if that mean wave has been found, you're in business just to use it. That's like doing homogenization, basically, low frequency. So you're okay with homogenization if there really is only one wave that you need to worry about, or at least the expected number of waves to worry about. But at higher frequencies, you don't get a very good prediction. Even if you know the dominant wave accurately, you need to know everything. And that says something about the limitation of employing any local approximation, I think, for effective properties. Okay, so there you go. I've done all this work on effective properties, and now I'm exposing a limitation. Actually, I'm exposing it quite quantitatively, admittedly in a simple case. Now, what else could you do? Well, you could allow for other correlation functions. You could allow the moduli to vary. You could do full elastodynamics. They could all be done, but it would be work. Different kind of remark. I mentioned a funny system, acoustics. Displacement U is a scalar. In fact, I can map this displacement, what I'm calling displacement, onto the pressure. And then the modulus would be like specific volume, and the mass density would be like compressibility. So for conventional acoustics, if I wanted to do real acoustics, using pressure, the results would all apply, except they would be for a composite with uniform density, but varying compressibility. Now, finally, I'd like to make this comment. All mean disturbances decay with distance from the interface. So I can't really talk about energy propagation. I don't know what's happening. And I think it would be very interesting to know what happens to the energy. Now, the only thing I can say on that subject is this. This methodology that I used didn't just give an expression for the mean waves, it actually gave an approximation for a proposed approximation for the polarization field in any realization. So I could use that formula, and instead of plugging into the variational principle I showed you, I could calculate using that formula, for instance, the energy flux. And then I could average the energy flux. And I think it'd be quite interesting to do that kind of thing, but I'm afraid that at my time of life, I'm rather reluctant to do the heavy calculations that might be involved. Anyway, with that, I'm finished. Thank you for your attention, and I hope that I've not spoken for too long.
Thank you so much, Professor Willis, for this really wonderful talk. No, you were not doing too long. It was just a bit over 50 minutes, so just perfect timing. And I'm sure we will have lots of questions from people attending your webinar. So please, people, come forward with your questions.